Good evening, everyone. This is Robert Paltz, and we're getting ready to take and go through the fourth video on the moon base service, the SLC Sub-Lunar Closed Loop Moon Base Service. And actually, this is the 2025 version. Uh, this is a collaboration. It's science fiction. So I take some liberties in it. I hope the viewers will contribute their ideas, and I hope the resulting collaboration is something that's a workable solution. Breaking from the traditional sci-fi uh, traditions, I'm writing this as a business plan and a marketing plan and a sales plan because that's what I'm used to doing. So I'm doing it that way. One of the collaborators I'm using is AI Ernest Gemini. Another one that I'm using is William Paltz, who's my brother. He's an ex-engineer, well, an engineer, retired engineer, and he's found it interesting enough to take and give me some help, and I've been appreciative of that. Um, Please like and subscribe if you receive notifications of future installments of this sci-fi business plan. There is the playlist, and I will be putting this under that playlist when I get through. Like I said, comments are gratefully accepted, and there's my brother's appreciation. Okay, the contents have been expanded a little bit now. You can see where the URLs for the previous versions are. So if you want to take and do this in sequence, the forward, which was done, it's the third video, is out, and then there we have the sublunar closed loop moon base summary, which is quite as I said in the forward, this is an iterative process, and the summary is going to have to be updated. Well, actually, it's updated in the book. It's just not updated on the video yet. And then we did the lunar lander. We brought it out, and today we're going to do SF0004, the first payload. Just so you know where we are on the timeline for this program. And you'll notice this is new, been updated, and we're SF4. So we come in right around here, and then we go all the way down to here. Okay. And okay. Actually, we'll probably go down to here. Okay. And so let's go back to the book. Okay. Just to bring you up to date, here's all the information. We'll page through all this. Don't get dizzy on me, because this is the current versions, and you can slow down and read it if you want to. Uh, they will be going back into the thing. Okay, we're going. This is what our delivery ship looks like. It's rectangular instead of circular. It has rockets on the end of it, and it has rockets on the side of it for landing. It has a pyramid front, and it has solar panels down all the sides. That's one rendition of it. Uh, Here's another. So you'll see I'm using pipes that will be then everything in this ship will be recyclable. So that's part of the plan. So you'll see that you have solar panels on this is the roof view, top view. And so you have solar panels all the way down it. These pipes actually extend all the way down the length. They are the drill pipes, and we'll talk about drilling, taking core samples to make sure that we're safe. And then we have skids down below, and that's water pipe. So that'll be eventually be water pipe in the institution. Okay, first payload at the site has been delivered. It's in the northwest rim plateau of Shoemaker Crater. It arrives on September 1st, 2030. That's kind of when I'm planning. Most of the stuff needs to be in place by then. We're using a lot of new technologies that won't be available until just before then. Physical condition, this is a 52 metric ton MRLL. We've lost about a half of the weight of it with the satellites and the AI data centers that we've taken and launched. So we have a fully working network out there, but we're landing on the moon's surface. There's no landing pad yet. That's going to be one of our priorities. So we did a belly landing. We ended up 10 centimeters below the original surface. That's roughly looks like this. So it's about half the pipe that we're doing there. High velocity exhaust fumes cause the surface scarring, and the solar panels have sustained abrasions, resulting in reduced electrical output. So that's where we're at, and we haven't opened the door. We haven't done anything yet. Fuel reserves are 75%, so that's for refueling stuff and for the hoppers and stuff like that when we get hoppers fixed up. This is at this point in time, this mission is 100% robot driven. There's no humans on the moon, and it will be that way until 2032 with the current plan. Our objectives at this phase of the program is to verify the proposed tunnel location is safe to proceed. There's a lot of concerns about whether we start tunneling and the tunnel machine gets all bound up because we hit voids or we hit hard rocks. So we will be boring into the surface of the crater and going in at least 25 feet. 25 meters, I'm sorry, to take and verify that's correct, that's safe to take and drill there, tunnel there. And so before we set the tunneling machine up, it's not there yet. It's not on this ship. We will be going in there. We're also going to be identifying water and sulfur resources in the crater. If we have sufficient sulfur, the lining for the tunnel will be sulfurcrete, which is stronger than concrete and doesn't require water to take and set up. And where we're building the landing pad right now is going to be a glass-like substance that is basically melting the surface material to the point where it flows, and it's something like glass, like if you were to take and melt sand on Earth. Okay. And we also want to take a look at what the water resources are in this crater, because that's paramount for taking and doing refueling operations. So we're trying to take and verify that we have the resources to take and do what our business plan is banking on. We're going to construct a landing pad that is capable of multiple landings, vertical or horizontal, for a ship of 100 metric tons. That's our current goal. Like I said, that's going to be made from the material that's on the surface. We don't know whether we have sulfur or where to find it yet. We're also going to take and construct the solar power plant. We need that actually before we could do the landing pad, so we can charge up the 3D printer that does the landing pad and the machines that feed the 3D printer. The data centers are all radiation hardened, and satellite communication systems are for commercial telecommunications surveying missions and low Earth orbit. So we have a revenue stream from our data center. We can start selling that to other people that are on the moon. So just like you would have an antenna on Earth and deal with one of the satellite companies like Starlink, you would buy a antenna system to take and connect to our data center, and then you would have a VPN to take and do it. Now, since we're not on Mars, we're not limited by concerns that some countries are better than others or so on. So all countries can take and use this system, and it will have VPN in it so that the system does that. Now, when it comes to Earth, that may be a different situation. But as it is now, and since we're doing laser communications to Earth, and we have two AI centers up there, AI data centers up there that are managing those communication centers. There's no reason why we can't have multiple lasers pointing towards Earth. Okay. We have some concerns. The material in the crater may not support tunneling. That's the reason why we're taking them and boring holes in there. You'll see these pipes right here. These are our boring pipes. They will have diamond heads on them, just like you drill for oil. And the boring machines that will be mounted on the robots will be able to go vertical or horizontal. So once we're through with this, we can sell this as a service. But at the moment, we're not ready to do it. And then there's not enough water to support the refueling business. Like I said, that's a concern. Surface manifest. This is after landing. We have 6 core Earth escape transit engines that are we're going to reserve those for deep space vessel construction and repair. We have 8 landing motors. 4 of those are going to be assigned to the first hopper that's going to be made from the pyramid on the front of the machine or the front of the lander. Fluid infrastructure, we have 12 storage modules containing the remaining propellant. So that's the beginning of our gas station. And there's equipped with flexible distribution lines because we had to have those to refuel it when we were in low Earth orbit, and we also had to have those to hook up to the landing motors. So we have quick connect connections and piping for taking in and setting up a refueling and the tanks, and they're 75% full. We got that 75% because we took a real low cost method of arriving at the moon. It took us 4 months, but we're here. 2 robots are configured to take and do core drilling. Like I said, they can do horizontal or vertical. And it's going to, their primary function is to take and verify the safety of the proposed tunnel location. Note the 34-foot meter drill stock for drilling doubles as guide rails for the robots on the outside of the MRLL. When I showed you where those are, they're up here on the top, right across there. They can be down here. This is a proposed engineering drawing, so don't take it as the final version. In fact, all these drawings you'll notice today are different, and they're different proposed versions of this concept. They double as guide rails for the robots on the outside of the MRLL when they're installing the 8 landing motors, and also they're out there for deploying the satellites and the data centers and the ion propulsion units. So basically, the robots can take and ride up and down those pipes and use them as like a railroad track, uh, and deploy the materials that they need to deploy when they're working on the outside. When they're working on the inside, the same clamps. You have 2 sets on each robot. The same clamps can be used to take and hook to the girders inside. So you can hook to the girders or you can hook to the pipes on the outside. And they're separated far enough that you can take and walk around the corners. So that's how you get to the outside. Robots are perfectly capable of moving themselves in and out without having a continuous track in both of them. 2 robots are configured to do a geographic survey the crater to determine the volume of the water resource and the sulfur content of the crater. Those are 2 of the items that are on the top of the list. There will be many more items that we want to look for. Note the core drilling robots, not expected to spend 100% of their time drilling cores. They're expected to finish that job relatively fast when they get to 25, 30 feet. And we're talking about a number of holes, maybe as many as 6 around where the tunnel is expected to go. But once they're done, then we expect them to take and be available to take and do more geographic surveying. Because two robots, there's not going to be enough to take and survey a 51-foot or 51 meter meter crater. And so um, you're going to need additional robots. We'd like to have more than 4, and eventually we'll have, but that's probably all we can take and assign in this first trip. Automation Suite is a 1 industrial 3D printer configured for Regolith, Sithering construction, and sulfur concrete. So it can take and do either. We just don't have the sulfur yet to take and do the sulfurcrete. Two advanced surface system operating robots, RASSOR units. I'm going to get used to that name eventually. Configured to excavate and feed raw oregano to the printer. I never say oregano right, correct. To the printer for construction of landing pads, access roads, and surface shields. Okay, that's these are blast shields for the around the landing pad to protect assets. And we have the landing pads. Like I said, this will be a glass-like structure, and I've given the thicknesses of these in other locations. Power tool and assets, reclaiming solar panels from the MRLL and transferring them to the crater. You'll notice that it's the top and the two sides have solar panels. That's going to be the bulk of our solar panels. They'll be transferred to the crater rim to build the primary surface power station. Now the batteries, all the batteries and are envisioned to be robot batteries, and they'll be hooked in parallel, so they can be on the power station or they can be on mobile assets. Okay. Manifest includes structural parts and a 3-year supply of standard components to mitigate predicted first-year mechanical failures. So our repair parts are there, our tools are there, and the solar panels are being reclaimed from the sides. We will fill, after we get the 3D printer in there and all the things that we have assigned, we will fill the rest of the 100 metric tons with whatever's available, standard battery packs, parts to build robots with, robot arms, robot motors, robot tires. So we will start building our inventory of standard parts, and that will stay inside the MRLL until we have the tunnel so that we can have this in a dust-free environment. So about 1/3 to 10% of the MRLL will still be available on the surface after we've pulled everything out of it. That's the current plan. Initial activation sequence, the nose cone, which is a pyramid, will it holds the MRLL nose cone holds 4 heavy-duty winches aligned with the primary structural legs. 3 are rated at 900 kilograms capacity, and 1 is rated at 5,500 kilogram capacity. So we can take and lift, for instance, the 4 corners of an object when we're pulling it up into the cone, and it's now a hopper and hopping to different locations. So this will be an 18-foot high cone, 18-foot high hopper when it's fully configured. Robotic egress, the automatic port cycles open on the upper nose cone. There's a port on the pyramid on the top. The internal robotic gantry units egress to the exterior hull, removing the standard mechanical fasteners, securing the nose cone to the main body while leaving the pyramid top hinge intact. Okay, so basically this is like a clamshell. If you remember some of the airplanes, the front of the plane would fold up, and the cargo would then come out of it. So that's what this is doing. Okay, and so you have that going on. We're basically using the 5,000 kilogram capacity hoist to raise this up. That may be overkill. We may be able to do it with a 900 kilogram. Just not taking any chances. The weight is considerably less on the moon, but we've got the big hoist, so we'll use it. There's an anchor point about halfway down the MRLL, and that hoist will anchor to that. And then when the bolts are released around the 2 sides and the bottom, only the hinge is holding it at the top. The hoist will activate, and the pyramid will go vertical instead of horizontal, and it'll be open. And now two legs will be added to it. They're the first things on the front of it to pull out. And so now you have two legs holding it down, the hinges holding it to the MRLL, and you can take and run pulleys down those legs and pull material out using this. So that's how it will take and do. And since the robots can ride on the girders, they can ride on those legs also, because the legs are nothing but girders that are closed a little bit for the angle of the pyramid. And so they'll be able to take and ride down there, install those pulleys, bring the cables down there, install those pulleys, and then take the ends of the hoist into the MRLL, and you got four hoists or three hoists that can take and pull it. Well, now that you got the legs installed, you also use the 5,000 kilogram capacity hoist to take and pull material out too. I don't envision needing that for the 3D printer, but that would be the heaviest object in this load. Mechanical opening, the robotic manipulators will route the 5,500 kilogram high tensile strength steel cable through the nose cone port, securing it to the designated anchored surface on the main hull. High capacity internal winch activates to run the cable taut and swing the nose cone upward along its hinge to expose the primary internal cargo bay. Crane conversion, two legs extensions are uninstalled from the nose cone, installed. Make a little mistake. In the nose cone, using they're pulled out of the nose cone using the 900 kilogram winches. The robotic manipulators attach these extensions to the primary structure of legs. I go back down and install it again. It's not the nose cone, but it's the MRLL. There we go. Yeah, it always helps to read these things. Robotic manipulators attach these extensions to the primary structure of the legs. These extensions incorporated heavy surface landing pads. In other words, they got pads designed to take and accept standard electric motors and wheels to provide local crane mobility. So we can put wheels on the bottom of these extensions. We've got two more of these extensions buried farther down in the MRLL, so we can have four of them, and we can also attach the four of the motors of the landing motors to it, and we put fuel tanks up on the top of it, and now we have hoppers. These wheels can later be replaced with standard landing engines. Okay, there we go, the landing engines, to convert the crane to a flight-capable hopper. Unloading and general purpose spot, the LMGPB assembly will crane winches unload the internal cargo. The robotic assembly line uses standard parts to fabricate a lunar module and general purpose spots. Each standard LMGPB is assembled with, well, all these acronyms are going to get me. It has one standard structural base plate, four standard girders for structural elevation, one standard solar voltaic panel, one standard battery. It's rated for 24 hours of continuous operation of the robot. One universal program controller board equipped with four integrated cameras and a satellite telecom node. The controller boards come automatically with a satellite telecom connection. And also they have Wi-Fi for when they're working inside of the tunnel. Four standard robotic manipulator arms are part of it. They have those tool couplers installed on them. And that's their option because they'll be assembling and disassembling stuff. and 4 standard electric drive motors and 4 standard wheels. So this is a basic robot. This then will have science packages added to it. It will have, the first 4 robots that are going out and doing surveys and doing boring have all these same parts in them plus more. So as you add more to it, the robots will have more. So this is a fairly good size robot. It's 2 meters long and 1 meter wide, and it has 4 wheels on it and 4 arms on it, and it can have 4 cameras integrated around, so you can take and see each arm can have a camera on it. Other cameras can be mounted on the base and view the arms working. Whatever the application is needed. Surface power infrastructure setup. The new assembled LMGPP systematically dismantled the exterior solar panels from the MRLL fuselage and transfer them along with the modular battery packs to the primary power station site on the crater rim. The LMGPBs integrate these panels with the support structures pre-printed by the 3D printer. So they will be moving panels up there and stacking them up until the 3D printer makes the infrastructure at the proper angle for the solar panels to operate properly. So since we don't know what the angle is going to be until we get there, the AIs and the 3D printers will have to communicate this and figure out what that is. They'll make the angles, and then the panels will bolt to those supports. I see them as columns in the crater rim. The place where we've chosen to put the power is in sunlight 99% of the time. So it'll be able to generate sunlight for a large period of time, generate power for a large time. So this will be the central recharging hub. Oh, by the way, this central power structure, if everything works out and the tunnel goes where we plan on it going at this stage, it'll be the power infrastructure will be on the crater surface, very near the entrance to the tunnel. So we will have very short power cables. The power station serves as a recharging hub for the rasters, the 3D printers, and the robot fleets that are on there. That's all we have. It's being recharged right now. The final crane conversion and sealing, once the standard parts for the LMGBPs are fully utilized, the remaining 2 extension legs are mounted on the nose cones. 4 electric motors, 8 standard drive wheels are fitted. I'm putting duals because this thing could be lifting heavy loads, and are fitted to the base crane extension. Right now, we got a mobile crane, and we're putting 2 battery units on it because it's going to be, it's got winches on it, 4 winches on it. It's got the motors on it, and it's probably going to be carrying heavier loads than anything else. When the LMGBPs are finished with the collecting all the stuff that's going to be used immediately, it takes the 8 landing motors off the outside, puts them inside the MRLL, the landing vehicle, and it inflates nitrogen bladder seals around the cargo way that take and keep dust out. So basically, we have a storage unit. It's depending on how things go, it could be as much as 1/3 of the LRMM, MRLL, the landing vehicle, or it could be 10%. Whatever's there, the nitrogen bladder seals will seal it off. Okay. A lot of the pieces, the girders and stuff like that, won't be needed until we start doing the tunnels. So you might as well just leave them there and let them sit there. Civil engineering operations, the raster units clear the designated landing pad area and transport excavated Regolith to the 3D printer. So when they're clearing it up, they're picking up the Regolith and they take it to the printer. So they clear off a spot, the printer starts printing there, they bring the material to it to take and be printed. The 3D printer executes a 3-layer 30, here's the thickness, 30 centimeter feathering print to create a heavy landing pad rated to support a fully loaded, that's a 100-ton, metric ton spacecraft. The raster units and the 3D printer then extend operations upward, paving a 1-layer 10-centimeter access road connecting the landing pad to the proposed subsurface tunnel entrance. That road's mainly going to be used to move the tunnel boring machine. I I'm a little, it's a little leery of running it on the surface because it's so heavy. And it's going to be very close to the 100 tons, even though we're going to break it down and we're going to make it out of light materials. But that road is going to be the primary access for going up there. Okay, storage and shielding considerations. The 3D printer constructs a 10-centimeter thick reinforced storage facility along the access road, leaving sufficient clearance for the tunnel boring machine cutter head to pass. So it can't be too close to the road. A nitrogen inflation pattern is installed as the primary pressure door. Now we're using those bladders as that are used to take and hold everything in place as primary seals. So near the landing pad, the printer constructs a second 10-centimeter thick storage vault and blast shield to store 24-core Earth escape engines. We only have 6 right now, but the plan is to have 24 stored there, and 48 liquid oxygen methane propellant units. So at that point, we would have that much oxygen and methane storage units. If we can take and fill those up and for refueling, we can make some really good money. Complete with paved roads and integrated piping runs for the automatic refueling system. It's feasible that the oxygen and methane tanks could be mobile units and come out for fueling and then go back in this protected area. The other option is to take and pipe it out. So we'll see what works when we get there. Geological exploration 4 standard are fitted with modular genealogical kits and programmed to execute surface surveys, radiation updating from the planned tunnel entrance and four perpendicular directions. So these are 4 additional robots in addition to the 4 that we originally put out that are now going out and doing surface surveys. These were used to disassemble everything and assemble everything in the first stage. So now they're surplus from that job and they're being redeployed to this job. So we will have 8 robots exploring this crater and trying to get a hand on what resources we have. What did we buy? Okay. So that's it. At that point, we will be doing gate reviews, and we'll have information about gate reviews later on. So we'll have we'll do a gate review when the landing pad is done, and we know about the tunnel entrance is safe, and we know how much sulfur we can take and depend on, and some idea of how much water. I don't think we'll have enough time at this point to have done a complete survey, but that's where we'll be. So anyway, I like our little lander. Let me put it back up here so you can see it. That's one view. Well, I like the other picture. Where is it? I like this picture of it. This rendition of it. I think this is closer in my mind. What I think the lander will be like. It's got its fuel tanks here. It's got the engines here. Here's the solar panels. These will be 34 meters long. This will be 34 meters long. And if we do it right and we forecasted it correctly, the pipes will be only about half submerged in the moon Regolith, and so this will easily open, swing up, and open up first. Okay. All right. That said, looking forward to everyone looking at it and telling me what they think of it. Of course, this is sci-fi, so remember it's sci-fi, but we would like to have something that's actually feasible. So have a good evening. Thank you for viewing, and I appreciate any comments you have.